So, good afternoon, everyone. Uh, am I audible? Okay. So, good afternoon, everyone. I am Devarun Banerjee. I'm a PMRF scholar from IIT Delhi, and I'm going to be your PMRF NPTEL TA for this course for this semester. In this course, we'll talk about basically about the thermodynamics, the system, chemical engineering, reaction system. So, I think there's Rohan. So, can you briefly tell about yourself, Rohan? Okay. So in this first week's lecture, we'll basically discuss about the basics of thermodynamics. So what we mean by thermodynamics is basically it is something which deals with energy and its transformation. So energy can be of different types. It can be of chemical energy, mechanical energy, electrical energy of different form. And what thermodynamics particularly is able to tell us is the direction in which the transformation can happen in nature. Okay. For example, in a chemical uh, chemical transformation, if the thermodynamics tells us the feasibility of the reaction, whether from A to B we can go by natural process or by some uh, external energy source or not. So it tells out about the direction in which the changes takes place in nature. It determines the conditions under which the proposed change attains a state of equilibrium. So if A to B is possible, then if it's then also there is a possibility that B can again get back to A. So when there will be equilibrium, it means that there will be the rate of formation of B from A and rate of formation of A from B will be same, right? So I can see. Can you guys briefly introduce yourselves, Tanay, M, and Rohan? Hello, I'm audible.
Hello, hello.
Yes, yes, yes.
Am I audible, sir?
Yeah.
Yes, sir. I am Rohan Krishna. I'm a third year student in Manipal Institute of Technology,
So,
Department of Chemical Engineering.
have you read about the thermodynamics, chemical engineering thermodynamics?
I didn't get you, sir.
Have you read the subject in your BTech studies so far?
Yes, sir.
Okay, okay, that's great. Yes. Okay. Tanay M. Okay. So, this is basically thermodynamics. It is something which is used to describe the processes in which properties of matter undergo changes and to relate these changes to energy transfer which accompany them. So as I told that obviously when there is a chemical transformation or any other type of transformation in some particular material, there will be properties change, and we will try to relate that change in property with the energy transfer which accompany them. So what are the um, things? What are the subsets of the thermodynamic calculations? One is the system. In this, there is a system. The system is basically of the substance with which we're doing the thermodynamic analysis, or a group of substances, which are we are particularly have interest, and it can be a particular reactor, a distillation column, a heat engine, or like that, any kind of unit operation, right? So on that particular system, we'll have to check the thermodynamic analysis, whatever there is a Gibbs free energy change or enthalpy, entropy change, whatever parameters. Now, obviously, there is a change as I talked. So, what kind of changes is taking place in that particular system, the distillation column or reactor or heat engine, etc., etc. So, that particular change is called as a process. For example, there can be a hydrocarbon and oxygen in a combustion chamber. So, this will be a system, and the combustion of fuel. So in the combustion chamber is a system, and this combustion of fuel to form water and carbon dioxide, it's a process, right? Now, the part of the universe outside the system, separated from system by system boundaries. Okay, so from the surroundings, the differentiation of the system. So that differentiation is done by the boundaries. So these boundaries can be physical, imaginary, rigid, or movable. Based on that, we actually differentiate those in a, it can be a closed system, open system. So for a closed system, what happens is it can exchange energy with surroundings, but not matter or mass. For example, batch reactor. So in a batch reactor, there will be obviously it when it's open to atmosphere, there will be some energy exchange. It is by the normal atmospheric uh, conditions, it will be getting uh, heat transfer. So, but there is not a mass transfer. There whatever product or reactant is inside the batch reactor, there is not a change in the product concentration with respect to the surroundings. On the other hand, a flow reactor or a continuous reactor is defined as the open system, because it can exchange both energy and matter or mass with the surroundings. Okay. Uh, Further classification can be like homogeneous system properties in the homogeneous system. So basically, the all the properties are same throughout the entire system, or it can also be called as a phase. So, for example, some liquid water in a beaker, a column of dust-free water, dust-free air is a homogeneous system. But if there is a solid catalyst in a liquid reactant, it may be liquid water, but this solid catalyst doesn't get mixed or isn't soluble with the water. It means that there will be two or more distinct phases. One will be the solid phase, another will be the liquid phase. So this mixture or this um, and overall system is a heterogeneous system because there will be multiple number of insoluble phases, and these are separated by phase boundaries. Okay. And obviously there will be some sudden change in properties at the phase boundaries. And apart from that, there is also isolated system, like uh, neither energy nor mass transfer would be there across the boundaries, and it will be absolutely unaffected by the changes in the surroundings. So there are certain specifications as pressure, volume, temperature. which are very much necessary to define the conditions of a given system. This kind of conditions, which are defined by different in such specifications, are called the state of the system. And variables which are used to define the state are called the state functions or system properties. Okay. And the minimum number of such variables required to represent the state is called the degrees of freedom. Okay. So there are some properties which are dependent on the mass. These are called the extensive properties, such as mass, volume. Okay, but so the total value of any extensive property is the sum of the values of the properties of the individual components. It's a very straightforward. If there is a maybe one entire system is composed of two materials A and B. So the mass of A and mass of B will be summation of this will be the mass of the entire system. But intensive properties are some properties which are independent of the size or the mass of the system, such as pressure, temperature, density, okay, specific volume, like that. So you cannot say like A has this temperature, B has this temperature, so add them and so the entire system will have this temperature. This is not like that. Okay, it's much more complicated. So it's depending on the other properties. Like this, there are other some functions as well, like state function. So properties of a system which describe its present state and do not give record of its previous history. So it's basically fixed for a particular state of the system and it is not dependent on the path by which the state was arrived at. Okay. So it's so if we have a circular system or a cyclic process, the change in the state function is zero. So if we consider a system, it's considered of in two different states, A and B. So the difference in properties between the two states depends solely upon these states and not upon the manner in which the system changes from one state to another. Okay. But on the other hand, there are other functions such as like that path functions. So it depends on the path from initial to final state. For example, heat, walk. So what is meant by the path? Path is a succession of the equilibrium states passed through when system changes from one equilibrium state to another. They are not, these are the path functions are not exact differentials. They are inexact differentials. So, for example, for a gas, if we do the volume of the gas changes from initial value V1 to V2, the ultimate equation comes as W equals to PdV from V1 to V2. Okay. On the other hand, heat. Heat is some quantity which is transferred between the bodies due to differences in temperature existing between them. Can't be so heat can't be stored as such within the system, and heat is usually absorbed or evolved only during the change of state of the system. Um, Energy is such a system. which can be stored in the system and can be exchanged between the system and surroundings. Exchange of energy occurs either as heat or work. Potential energies is a form of energy which is possessed by the system due to its position above some arbitrary reference line. Okay. For example, potential energy is equals to mgz. M is mass, z is the height or elevation above the ground, and g is the acceleration due to gravity. And kinetic energy is such energy is the energy possessed by the system by virtue of its motion. Kinetic energy is half mv square or mu square. U is the velocity and m is the mass. But if you see the kinetic energy and potential energy, these are not thermodynamic properties of the system because they don't change with the change in temperature or pressure of the system. But internal energy, which is the energy possessed by the system by virtue of the molecular configuration and motion of molecules, is a thermodynamic property of system. So it is a function of temperature and pressure. Now you have the steady state. So steady state is a system which is interacting with the surroundings, said to have attained a steady state condition when the properties at a specified location in the system do not vary with time. So if we consider the walls of a furnace whose inside surface is exposed to hot combustion gases and outside surface to atmospheric air, heat transfer occurs from inside to outside. At steady state, what will happen? The temperature at specified point in the wall will be constant, even though the temperature at different points would be different. When the system at steady state exchanges mass, heat, or work with surroundings, even when exhibiting time invariance from the property. There are also called as an equilibrium state. The properties are uniform throughout when it's in equilibrium and it do not vary with time. So there can be thermal equilibrium, there can be mechanical equilibrium, thermodynamic equilibrium. Okay. And in this case, what happens is all forces are in exact balance. The state of equilibrium will be retained by the system for any small, short mechanical disturbance in external conditions. If we have a Gibbs phase rule, it gives the relation between the number of degrees of freedom so it's governed by this rule called Gibbs phase rule. It gives the relation between the degrees of freedom, distinct chemical species constituting the system and number of phases present at equilibrium. So F equals to C minus P plus 2. So along with that, there is a the zeroth law of thermodynamics called as if a body A is in thermal equilibrium with B and B is in thermal equilibrium with C, then C is also thermal equilibrium with A. So there are two types of processes: reversible process and irreversible process. So these processes occur when there exists a driving force or a change of state between the parts of the system. So if there is a finite driving force, the process is irreversible. And if it's infinite in magnitude, the process is reversible. So irreversible process, it can be reversed without the use of external energy. So to bring back to initial state, surroundings have to undergo some change to heat or work interactions. The changes remain in the surroundings or in the system after the process. The changes remain in the surroundings or in the system after the process. So, for example, all spontaneous processes, free expansion of gas, diffusion of solute from concentrated region to dilute region, transfer of heat from hot body to cold body, rusting of iron, mixing of gases, these are all irreversible process. The reversible process means the direction of process can be changed by an infinitesimal change in the forces acting on the system. Can be brought back to original state, leaving no change in the surroundings. Can be brought back to the original state, leaving no change in surroundings. So a reversible process takes infinite time for completion. Uh, the complete absence of dissipative forces like friction, and it's actually never attained in practice. Example is a process very close to a reversible process consists of water and water vapor in equilibrium in a cylinder provided with frictionless piston. The external force on the piston is kept equal to the force due to vapor pressure of water at a given temperature. So by increasing the force acting on the piston by an infinitesimally small amount, the vapor will condense. The work required to condense a certain amount of water vapor would be equal to that required to vaporize the same quantity of water. With this, we come to the first law of thermodynamics. So, what does first law tells is although energy may be converted from one form to another, it can't be created or destroyed. Whenever a quantity of one one form of energy is produced, an exactly equal amount of another kind must be used up. Okay. So for a cyclic process, this first law of thermodynamics is like for a system undergoing a cycle of changes, the algebraic summation of all work effects exactly equals the summation of all heat effects. So Q is heat added to the system, so it would be positive when heat is added to the system and negative when heat is rejected from the system. W is the work done by the system. So it will be positive when work is done by the system and negative is work is done on the system. So if the units are consistent, summation of W will be equals to summation of Q. Okay. So the energy possessed by the system by virtue of we have covered this internal energy thing. So for a closed system, what will be so delta E system will be the change in kinetic energy plus change in potential energy plus change in internal energy equals to Q minus W. If it's a steady state non-flow process, means no change in kinetic and potential energy, so there will be only change in internal energy. So delta U equals to Q minus W. So differential change means du equals to dq minus dw. For an isolated system, dq equals to 0, dw equals to 0, thus du equals to 0. So if a system is kept at constant volume in which no work of expansion or any other kind of work is done, the change in internal energy equals the heat supplied to as the work of expansion is 0 for constant volume process. du equals to dq. When the system is free to expand against a constant external pressure, the change in internal energy is no longer equal to the energy supplied as heat. So H equals to U plus PV. So the heat supplied at constant pressure can be measured as the change in another thermodynamic property of the system known as enthalpy. H equals to U plus PV. Okay. So dH equals to du plus dPV means dDV plus vdP. du is dq minus dw. So dw equals to pdv for a reversible non-flow process and vdp equals to 0 for constant pressure. So dh equals to dq for constant pressure process with only PV work. In this way, for flow process, this first law comes like this. delta H plus G delta Z plus half delta U square equals to Q minus WS. So delta H equals to Q minus WS. a constant volume process, du will be equals to dq minus dw. So if du equals to dq, or no work of expansion, dw equals to 0. So du equals to dq means it will be cv/dt. So the heat supplied is equal to the product of heat capacity and rise in temperature. Yeah. So du equals to cv/dt for a constant volume process. For a constant pressure process, similarly, dH equals to cp/dt. Okay. So if we rearrange this, so H equals to U plus PV, dH equals to du plus dPV. PV equals to RT for ideal gas. So du plus RdT, since R is a constant. Now can substitute. So dH equals to cp/dt, du equals to cp/dt plus RdT. dt gets cancelled out. So Cp minus Cv equals to R for ideal gas. For isothermal process, dW equals to dQ. So Q equals to integration PdV. Q equals to RT ln V2 by V1 means PV equals to RT. So V2 by V1 equals to P1 by P2. So Q equals to W equals to RT ln V2 by V1 equals to RT ln P1 by P2. So these are apart from that, there are some further like about the qualitative differences between heat and work, direction of change. These are basically points of the limitation of first law of thermodynamics, and then the second law of thermodynamics. So second law of thermodynamics is just a generalization of our experiences with spontaneous processes, and it can be stated in a number of ways. It cannot it cannot by itself pass from a cold to hot body. All spontaneous processes are irreversible and are accompanied by a degradation of energy. Every system, when left to itself, so there can be basically two statements. One is a Kelvin Planck statement, Another is the Clausius statement. So Pelvin-Planck statement tells that impossible to construct an engine that operating continuously in a cycle and will produce no effect other than the transfer of heat from a single thermal reservoir at a uniform temperature and the performance of an equal amount of work. This statement implies that at least two thermal reservoirs of different temperatures are necessary for an heat engine to operate. This is because only the part of the heat transferred to the engine from a high temperature reservoir is converted to work. The rest is rejected to a low temperature reservoir. Further, the statement implies that no heat engine can have 100% efficiency because heat cannot be completely converted to work. The word continuous in the Kelvin-Planck statement has an important implication. This is the isothermal expansion of an ideal gas. The change in internal energy delta U is zero in this process. And another is the Clausius statement. Impossible to construct a heat pump operating continuously will produce no effect other than the transfer of heat from a lower temperature body to higher temperature body. In other words, any process which consists solely in the transfer of heat from one to another temperature to higher temperature is impossible. Means that energy in the form of work must be supplied to the heat pump in order to transfer heat from a cold body to hot body. Therefore, the coefficient of performance of a heat pump can never be infinity. So if we consider a heat pump which violates the Clausius statement by absorbing heat Q2 from a low temperature reservoir and transferring it to a high temperature reservoir, so there is a heat engine that violates the Kelvin-Planck statement. There is a engine, it takes Q1 from high temperature reservoir and gives to the pump, which the pump takes Q2 from low temperature reservoir to and gives the heat to high temperature reservoir. Okay. So another one is the heat pump that violates the Clausius statement. So a pump working, taking heat from low temperature and giving it to the high temperature reservoir, and then the engine works taking heat from high temperature reservoir to giving to low temperature reservoir.